Okay, we're going to look at some of the examples of chapter 2, and I would like you to spend time and doing the examples that I'm going to do on a piece of paper, and try to work on the problems as I am working on it, as if that you're taking notes while you're in the class. For each problem, please go ahead and pause the video, read the problem, okay? Read the problem carefully. Write down what you have, just like I do, and then try to solve the problem as I am solving the problem, just like what I do, all right? So pause the video right now, read the problem first, and then play the video and work on it together, all right? Perfect. Now, we have a dog that has an average speed of 1.40 meters per second. So I know that on average, I'm going to just use a bar. I can write AV as an average here, but I'm just using a bar, meaning that I'm talking about the average speed of 1.40 meters per second for the dog, and the distance is 2.3 meters. So meaning that the dog displacement is 2.3 meters to get to to the owner. So the distance, or delta x in our case, is 2.3 meters. And how much time does it take for the dog to reach its owner? So now what I'm looking for delta t. Now, if you go to the equation sheet, by the way, I have provided a specific equation sheet for each week, and then an overall equation sheet that you can use. So if you're looking at the equation sheet, what's the V bar formula? It is delta x over delta t. So V bar is 1.40 equals delta x is 2.3, and delta t is missing. Now, just use delta t here. Don't use x. A lot of times that we want to solve a problem for an unknown, we use x, okay, to solve it, because x has this meaning of as if you're looking for something, okay, you're solving something for x, but x has a meaning here in physics. The other thing that's important that should watch is that you're not using a, for example, you are not using a question mark here, okay, and solve it for question mark. Just put delta t as if it was whatever that it was before. So you're not changing any type of formula here. You're using it as it was. So I have delta t, and I want to solve this for delta t. A lot of you have problems here, so I'm going to tell you what you need to do. A little bit of a equation box here, or math box, I want to call it. So if I have A over B equals C over D, something that I can do in mathematics, and it's allowed, is that I can change the position of these two. So kind of writing it as D over B equals C over A. So I'm just changing the position of A and D. You can do the same thing for C and B. It will still be completely correct. You can also write it in this way: A times D. So the other true formula is A times D equals C times B. Okay, and these two are in our benefit. Take a look at what we have here. I have 1 here at the bottom, right? 1.40 over 1 equals 2.3 over delta t. And if you're looking, this is the exact same configuration that we have here. So now I can solve it for delta t. All I need to do is to do this. So delta t over 1 is 2.3 over 1.4. Okay? Meaning that delta t Delta t over 1 is just delta t. Okay, 2.3 divided by 1.4. If you have a calculator, it will get you 1.6 seconds. So it will take the dog 1.6 seconds to get to his owner. Okay, this is a very, very, very important example. So let's take a look at this. Pause the video, read the problem first. Okay, now when you're reading this problem, write down everything that you have. So let's see what we have here. What we have, let me make this a little bit smaller. All right, now let's see what we have. So what we have is this guy starting from x equals t, moving very fast to this point, which is marked 50 meters. Okay, so we know that this distance is 50. Okay, and then walking back from that point, walking back to where it was started his exercise. So what we know is that the distance from let's see, initially it was 0, and then final is 50 meters away. Okay, and it took him 8 seconds to do that. So delta t here is 8 seconds. Okay, it is started from 0. It is started at x equals 0, at times equals 0. Then it went all the way to 50 meters in 8 seconds. Okay, now part A is asking the average sprint velocity. Okay, meaning that once it is started from this point all the way to this point. Okay, so let's take a look. The average velocity is delta x over delta t. Delta x is 50. Delta x is x final minus x initial, which is 50 minus 0. Delta t is the time it took it to do that. So it's 8 seconds. And the final answer is 6.25 meters per second as the average velocity, starting from 0 going all the way to 50, okay, on average. Now, part B is asking the average walking velocity as if it's coming back, okay? So that is for part A. For part B, the average walking velocity, I have again delta x, delta t, okay. Delta x at this point is kind of a tricky to understand. So delta x is x final, right, minus x initial. Delta t is t final minus t initial, all right? Now, x final, finally, once it's coming back, he will go back to where he has started, walking. So he will go back to 0. So now it's 0 is final position because eventually he will get back to where he has started. Okay, and initially he was at 50. Okay, delta t is t final, so the time at the final position, and once he get to time equals 0, is 48, because it took him 40 seconds to get to a starting position. So it took him 8 seconds before. Now it's taking him 48 seconds to get to the final. So 48 minus 8, or it's also given. See, it says slowly back to starting line in 40 seconds, 40. So it means I can either write 48 minus 8, or I can just write as it's as the time is giving to me. So I can just write 40 here. Oh, change the color. So 50 over 40, 50 over 40. Okay, so I can cancel out this 0 and this 0, 5 over 4. So V bar is 5/4, which is minus 5 actually, because it's 0 minus 50. So minus 50/4, which is minus 5/4 right here. And then it is negative 1.25 meters per second. Okay. Part C is asking us the average velocity for the complete round trip. So this guy has started from this point, and he went all the way, and then he came back to the initial position. Okay, so velocity of average is displacement delta x over delta t. Displacement, he started from this point, went all the way, and coming back to the same point. The displacement is 0 because the final position and the initial position are the same. So 0. Delta t was how much, what it was, whatever, it doesn't matter. Delta t is delta t. So 0 over whatever number that we have for delta t, which is 48, by the way. So 0 divided by 48 is just 0 meters per second. So his average velocity is 0. This is insane. This is very interesting. His average velocity for the whole round trip is 0 because he's not moved. He came back to where he started, and that's what we talked about in the lecture. If you start from your house going all the way to grocery store, okay, and then let's say that this is the grocery store. You went for shopping, and then you went to visit a friend. So you talk to your friend, and then you went to your parents' house, for example, whatever, to drop the grocery, for example, and then you went there, and then you came back, and it took you 3 hours to do that. So your delta t is 3 hours. Okay. If I ask you what the average velocity for you is, it is 0. The reason is delta x over delta t. Delta t is 3 hours, right? It took you 3 hours to do that. By the way, if you want to use this, you have to change this to seconds. So just make sure. But who cares? Because delta x is 0 anyway, right? You went to grocery, you went to visit a friend, you went to visit your parents, and then you came back to where you were before. So 0 and 0 divided by any number is 0. So your average velocity is 0. Okay, let's take a look at this example. It is another very important example. Pause the video for a second, read the problem, and come back to solve it together. Okay, so what we have is a cyclist riding in a straight line with an initial velocity of 3.5 meters per second. So what we have, I'm just going to write everything here. So what we have is V initially is 3.5 meters per second. So this will help me to see, memorize, summarizing the formula or the problem this way will help me to understand that. Remember from chapter 1, I told you 50% of solving a problem is understanding the problem. If you understand the problem, you can easily solve the problem. Easy. The main problem of most of the students, almost 99% of the students, is that they don't know what the problem is asking for. They don't understand the problem. You have the equation sheet. The equation sheet is like a toolbox for you. If you don't know how to use a wrench, for example, okay, if you don't know how to use a screwdriver, then that will become a problem. So writing things like that will help you to understand the problem and kind of streamlining. Okay, so V initially is 3.5 meters per second, and acceleration at, so acceleration of negative 1.0 or 1 meters per second squared, okay, for 2 seconds. So we know the time is 2 seconds right now. So, so delta t. So delta t is 2 seconds. Okay, so kind of like that. That's what we know about it. The cyclist then starts to continue. Take a look at this. Let's take a look at this first for a second. This is what we're talking about. Okay, so what we have is v versus t figure. Okay, so velocity versus time figure. And then what we have is that it started at this point with 3.5 meters per second, okay, right there. And it went down to something we don't really know what this velocity at this point is, but it took it 2 seconds to do that with a acceleration of -1. Now, remember from second chapter, I told you if you multiply a and v, if you get a positive number, that means you're accelerating. And if you're getting a negative number, if you multiply them, that means you're decelerating, you're slowing down, okay? So which one is that? You multiply them. So if I multiply them, I'll get 3.5 times -1 is a negative number, okay? Is a negative number, meaning it will slow down, okay? And that's exactly what's happening. See, the velocity started off from something big and it drops down because right now at this point, the velocity is between 1 and 2. Whatever it is, it's between 1 and 2. Okay, so if I want to take a look at this, if I want to take a look at this problem, I can easily find the final velocity. Remember this formula? Okay, v equals at plus v naught. If you remember this, all you need to do is to just put the information inside it. Final velocity equals acceleration times time plus initial velocity, okay? And I have explicitly explained how to derive this equation. You don't have to derive the equations. It's not something that your major is requiring or this course is requiring you to do, but just have the equation sheet in front of you and look for this formula. So v equals at plus v naught. And I can search for the final velocity at this point because final velocity is a, which is -1, t, which is 2 seconds. It took it 2 seconds to do that. Initial velocity was 3.5. So I have -2 plus 3.5, meaning that the final number for velocity is 1.5 meters per second at this point. So this point is 1.5. Okay. Now, it will, the second part of the problem is saying then the cyclist then will go with a 0 acceleration. So it means the velocity is not going to change at all. So it will stay the same through this motion, starting from 2 seconds, 3 seconds, 4, 5. It will still be the same as I found it for final. Okay, so through this motion, it will not change. But then, so this is with v being constant. Okay. Oops, my very bad handwriting. But v is constant through motion of 2 seconds all the way to 5 seconds. Then finally, it will accelerate at 1.5 meters per second square for additional 2 seconds. So for additional 2 seconds from 5 to 7, it will do some accelerations. So if you're looking at this, Now the initial velocity for this last 2 seconds, the initial velocity is the final velocity of the previous part, which is 1.5, right? Delta t is 2 seconds, and acceleration is, how much it was? 1.5. So 1.5 meters per second square. Now I can find the final velocity of that portion as well using the same formula, right? So final velocity is AT plus V naught. Final velocity is A, which is 1.5. T is 2 seconds, plus V of initial, 1.5. So that's why it's important to, this is why it is important to write down things that you have, because V of initial, V naught here, is 1.5. If you don't write things that you have, you're easily going to use 3.5, which is incorrect, okay? So now I have V initial, V final is 2 times 1.5 is 3, plus 1.5 is 4.5 meters per second. So that's the final velocity. So if I go back to this graph, it is started right here with a velocity of 3.5 meters per second. It ended up being here with a velocity of 1.5 meters per second. It took the same velocity, didn't change the velocity through all the way to this point. So this point will have the same 1.5 meters per second. And then it went all the way up to 4.5 meters per second, okay? So now we found the velocity of each point in this graph. At each point in this graph, we found the final velocity. So that's basically part A. What is the final velocity of the cyclist? So 4.5 meters per second at that point. Part B is asking, what is the average acceleration? What is the average acceleration of a cyclist for these 7 seconds? Average acceleration. I go to equation sheet and I'm looking up the average accelerations. Okay, let's take a look. Average acceleration. Average acceleration. If you don't remember, go ahead and check it out in the equation sheet. It is delta V over delta T. Delta V is final minus initial. Delta T is T final minus T initial. What is V final? Let's take a look. V final is 4.5 meters. So 4.5 minus V initial. V initial is 3.5 minus 3.5. How many seconds did it take? Okay, 7 minus 0, correct? So 4.5 minus 3.5 is just 1. 7 minus 0, 7, 1 over 7, okay? Which is, it's been already calculated. You can put it in your calculator, 0.14 meters per second squared, which is 0.14 meters per second squared. There you go. Okay, another example. This is also a very, very important example. Pause the video, read the problem right now. Okay. Now, when we're looking at this problem, it's actually a fairly easy problem, but it's important to you guys see this and solve it at the same time I'm solving it. Just don't look at the screen. Solve it with me. If you want to get an A in this course, you have to do as I say. You have to solve the problem as I am solving the problem. Okay. All right, let's take a look. We have a boat that is having a constant speed of 1.5 meters per second. So velocity was constant initially, okay, as 1.5 meters per second. And so then it starts to accelerate with a constant rate. So acceleration is 2.40 meters per second square, okay? And then part A is asking, how fast is the boat moving after accelerating for 5 seconds? So we know the T. So initially, T is 5 seconds. Is that right? Yes, 5 seconds. Now, you might say, why didn't you use delta T here? So here's the thing. So the boat is starting from this point, okay? And then it has some constant velocity to this point. At this point is the point that I count down the time. At this point, it starts to accelerate. At this point is the starting point for me. I don't care how much time it took it to get to this point so it can accelerate. This is the starting point for me, and it took it 5 seconds. So I want to know what's the final velocity is after 5 seconds. So 5 seconds. So I can now write delta T equals 5 seconds here. Now, if you're looking at the formula, we have the same formula that we used for previous problems, Vt plus V naught, okay? Now I have A, which is 2.4. T is 5 seconds plus 1.5 meters per second as the initial, because this is the initial starting point for me. So if I do that, what I have is 5 times 2.4 plus 1.5 will give me the final velocity. If you put that in the calculator, you'll get 13.5 meters per second. Now, you might, what I'm about to say might be a little bit funny to you, but this is something that I've been doing when I was a physics bachelor degree or even master's degree. I have never used a calculator, being honest. I used to calculate everything in my head. And I believe that that's an exercise that you do. If you want to make muscles in your body, you exercise, you go to gym, right? You lift heavy things, for example. But if you want to exercise your brain, you have to stop using the calculators. You have to try to using it with your head. And it might be a little bit difficult, but I encourage all of you to do that. It's just a very good exercise because using a calculator is addictive. The simple math will be, you won't be able to do it because your brain is saying, hey, do the calculator, use the calculator. Okay, now that was part A, in fact. That was part A of the problem. Let's take a look at part B of the problem. It says, how far has the boat traveled in these 5 seconds? So technically, I want to know how far it's moved or what the distance is, what the displacement is, in fact, right? Remember the formula for displacement? Delta x equals half times a times t squared, right? Plus this. So if you do that, half is just half, 1 over 2.5, right? A is 2.4 meters per second. And t is just 5 seconds, so t squared is 5 to the power of 2, which is 25, right? So I have 5 to the power of 2, plus v0, v initial, 1.5, times t, which is 5. So times 5. Okay. So what I have here is delta x equals 1 over 2, 2.4. Let me tell you how I do it without a calculator, because you say, oh, I can't multiply the 2.4 without a calculator. So 2.4 is 24 divided by 10, right? 24 divided by 10 is 2.4. Instead of writing 2.4, I can just say 24 over 10. 5 to the power of 2, what is it? 5 to the power of 2. 5 times 5 plus 1.5 is 15 divided by 10. Okay, times 5. All right. Now, delta x will be equals to, if you're looking at this the way I do it without a calculator, I have 5 over 10 on each side. I can factor that out, 5 over 10. From the first one, I have 24. I have 2 in the denominator. I have an extra 5. From the first one, I have 15. From the second one, I have 15. So then I have 5 over 10. Okay. 24 divided by 2 is 12. 12 times 5 plus 15. Okay. 12 times 5 is 60, right? So this is 60. 60 plus 15 is 75. So 5 over 10 times 75. Okay. And now I can easily write down 5 divided by 10. What is it? Okay, 1 over 2, exactly. Times 75. Meaning that 75 over 2 is the final answer, which is what? 75 over 2. 75 over 2. So 70 over 2 is 35, right? 5 over 2 is 2.5. 35 plus 2.5 is 37.5 delta x. So it's meters. Okay, now I don't want you to waste time at the same time. If you're taking an exam, time is valuable. But this way is a good practice to, you know, kind of playing with the numbers and, you know, exercising your brain to do the calculations, things like that. This problem is a very, very interesting problem. So make sure to solve it a couple of times at least for yourself. Okay, next problem in our list. Pause the video, read the problem first, write down things that you have. Once you do that, we'll start working on it together. Okay, now that you have paused the video, let me go ahead and a little bit small, make this smaller. Okay, now we have a race car here. Starts from rest. This is the key. That's why reading the problem and understanding the problem is 50% of solving the problem. Awesome. So starts from rest, meaning that the initial velocity is 0. Thank you. Awesome. And starts from rest and accelerates at 7.4 meters per second square. So constant accelerations of 7.4 meters per second squares, meaning that in each second, it will gain 7.4 meters per second for speed, okay? Now, how far has it traveled in 1 second, 2 seconds, 1 second, 2 seconds, and 3 seconds? I'm just gonna use, I'm just gonna solve it for one of them. The procedure for the rest is the same. So we're asking for how far has it traveled? We're looking for displacement, okay? The displacement is half AT squared plus V0T. Now, what is V0? 0. So this term is 0 anyway. So I am having only one term, half AT squared. Half is half. A is 7.4, okay? T is squared. 1 second, for example, if you want to solve it for the first one. 1 second is 1, so 1 to the power of 2 is just 1. So I have half of 7.4, which is 7.4 divided by 2. What is it? I need the calculator? No, you don't need the calculator. 7 divided by 2 is 3.5. 4 divided by 2 is just 0.2. 0.4 is just 0.2. So you have 3.7 as your final answer. Boom. Easy as that. Okay. This problem is also very important because it is dealing with time-independent equation, one of the most important equations in chapter 2. Let's pause the video, read the problem, and come back. Okay, read the problem carefully. Come back to see how we can solve this. All right. So what we have here is a plane that is trying to take off, right? Plane A has acceleration A, so we know what the acceleration is. Acceleration is just A. See, it doesn't give you any number for it. Okay, that's fine. I can just use A instead of assigning a number for acceleration. I'm just writing it as A. Okay, and the takeoff is speed. The takeoff is speed, meaning that once it's taking off, takeoff speed, it doesn't give you a number for it again. So I'm just going to use it V of takeoff, TO. What is the minimum length of a runway requires for this plane? So the minimum is the length that it's taking off and leaving the ground. So do you have any information about the time? No. There is no information given about the time. It doesn't tell you, oh, it took it 30 seconds to do that. It was doing it in 20 seconds. And no, we have no information about the time whatsoever. So what it means is that you need a time-independent equation. So the time-independent equation is this. V final squared minus V initial squared is 2 times accelerations times delta x. Okay, now if you're looking at chapter 2, I explicitly show you how you can derive this equation. You don't need to. I have given it to you in an equation sheet, both for chapter 1, for week 1, and for an overall equation sheet that I've been providing for you on Canvas. Now, when you're looking at this, v squared minus v0 squared equals 2a delta x, there is no information about time in this equation. Okay, so now let's see what we're asking for in part A. It says, what is the minimum length of runway delta xa requires for this plane? And it says give a symbolic answer, meaning that you don't have to put numbers in this equation. You can just find it in terms of the others. For example, if I solve this for delta x, I can write delta x equals v squared minus v naught squared, v squared minus v naught squared divided by 2a. Okay. So initially when the plane starts, it starts from 0, right? You don't board on a plane who's moving, correct? I mean, maybe you do, I don't, right? So you don't board on a plane that's moving. You start from 0, so boom, this is 0. Now you have delta x equals final velocity, which is given. It says takeoff is speed squared divided by 2a. And that's our symbolic answer, really. If you want to find a, based on a number, that number will be given to you, okay? Which is exactly what's happening in part C, okay? Now, let's take a look at part B of the problem. It says plane B has the same acceleration, so A is the same, but requires twice the takeoff speed. So whatever that you put before for v of takeoff, you need to double it. You need to multiply it by 2. Okay, meaning that I have the same formula I have the same formula but my takeoff speed is doubled. So instead of t of takeoff to the power of 2, I have 2 times of the t to the power of 2. Remember, this 2 is also under the power. So what I have then is 2 to the power of 2 is 4. Okay, VTO to the power of 2, 2a. And if you're looking at this, have you seen this somewhere before? Have you seen this somewhere before? Yeah, it's right here, right in front of you. You've seen it before. So what I have is 4 times, this has a name, it's called delta x. For what plane? For plane A. Okay, so this is for plane A. This is for plane B. So delta x for plane B is 4 times of the delta x for plane A, because it requires to have a double of takeoff speed. Now, part C is asking, find the minimum runway length for plane A if A is 2.2 meters per second squared and V takeoff is 95 meters per second. So in other words, just substitute some numbers here. Instead of V of takeoff to the power of 2, put 95 to the power of 2 over 2a, just put 2 times 2.2 here, and then solve it. Easy as that. Okay, so here, I'm not going to solve all the problems, all the examples in the book, but I have it in this file, so you can take a look at them and work on it. For example, this one is also a very important problem. And also there is a solution for it, so you can take a look at them as well. Or over here, I have another problem, same type of formula that we used, time independent formula, okay? Now, the only thing about this particular problem is that the final velocity is 0 because it saw a deer and it wants to stop. So final velocity is 0. So that's why you're dealing with a negative here. Okay. So just pay attention to those, work on those. And, you know, I have office hours, so come and say hi and, you know, let's chat about them if you have any problem. Now, I want you to go to this problem. And pause this video, read the problem first, and try to solve it. Okay, as you're solving it, and then let's try to see if we can solve it together. All right. So pause the video first, read the problem, write down everything you have, and then let's solve it together. Okay. Now that you have read the problem, let's solve it together. I'm going to make this a little bit smaller. All right, let's take a look. We have a lemon drops from a tree and falls to the ground 3.15 meters below. So we have this height to be given, right? It is 3.15 meters. So this height is 3.15 meters. And how much time does it take for the lemon to reach the ground? So we want to know how much time it requires for the lemon to drop. Okay, now, and the second part is asking, so what I'm looking for part A is that how much time it will require. So I'm looking for T, the time that it took the lemon to hit the ground. And then part B is asking, what is the lemon's speed just before it hits the ground? So just before hitting the ground, just at the same moment it's hitting the ground, right with some speed, right? So we're asking for the velocity that the ground as well. Velocity. So we're looking for these two. Now, it's very important to understand that this is a free fall, and we talked about the free fall in our chapter 2 video, end of a chapter. Free fall is a motion with constant acceleration. So with constant a, and that acceleration is not changing because the gravity of Earth is the same, right? The gravity of Earth is, here in the United States is G, is 9.81 meters per second squared. Anywhere in the world is the same, close to the Earth's surface. So with the constant A, which is G, which is 9.81 meters per second squared. So we are dealing with a motion with constant acceleration, but at this point, the acceleration is just G because it's freely falling, okay? Free fall is a type of motion with constant acceleration, but that acceleration is being provided by the Earth's gravity, and that acceleration is just G, which is 9.81 meters per second squared, constant anywhere in the world close to the surface, okay? If you go really, really high in the sky, if you leave the Earth's atmosphere, this G is getting very close to zero. That's why if a lemon drops, it will never fall down, right? Because there is no gravity out there because the G is zero. So if you travel to a space station, let's say in future, or if you travel to Mars 30 years from now, right? It's possible. Then you will feel no G because obviously you're not on ground, so G is zero. So you feel no gravity, you're just way less, right? Anyway, so now let's take a look. What we were looking for is how much time it is required for this to fall down. So what we have, we're looking for time. So delta x is half a t squared plus v naught t, correct? Now, what I have is once the lemon is leaving the tree, it starts from zero velocity, right? It's at rest, it is hanging from the tree, and then once it's leave the tree, it starts from the velocity of zero. So this guy is just zero. A is G, so I have delta x equals half G t squared, right? What is delta x? The distance, displacement. And so in this case, it is towards the y direction, but we can still show it as delta x because it is up to us to choose the coordinate system. So I can choose the coordinate system, x being along, vertical direction. So delta x is 3.15, the displacement. Half is half. G is 9.81, right? 9.81. And t squared is just t squared, right? Now at this point, you can put this in a calculator. It's fine because you're dealing with the power and you're dealing with, these interesting numbers that we have here. It's okay, but at least know what you're going to put in a calculator. See what I'm talking about? So if I want to write this, and I want to solve this for t. So I am going to solve this for t, but how do I solve this for t? How do I solve this for t? Okay, a lot of you might have problems with this. I have seen many students struggling at this point, and how do I find t at this point? Now, let me give you this. A math box. Math box, okay? If I have A being equal, A equals, for example, B, something, okay? So this means this equal sign means that whatever that you have on the left-hand side is equal to whatever that is on the right-hand side. A equals B. A equals B. Whatever that you have, it's on the left equals whatever that you got on the right. Now, what if I double everything? Will that still be equal, right? What if I multiply this side by 2 and multiply this side by 2 as well? Would that still be equal? Yeah, they're just double, but they're still equal, right? What if I divide everything by 2? Would they still be equal? Yeah. So the point here is whatever that you do on the left-hand side, if you do the exact same thing on the right-hand side, it will still be okay. They will still be equal, okay? If you divide this by 1.1, if you do the same thing over here, divide this by 1.1, they'll still be equal. This equal sign will still be okay. It will still be correct. Okay, so what I have here, I want to solve this equation for t, but there are some stuff that are in our way. For example, I have an equal sign here, right? If I multiply everything by 2, I have 2 times 3.15. I have 2 times 1 over 2, 9.81 t squared, right? So what I have is this 2 and 2 will cancel out, okay? Then I can divide, so I have a equal sign that is still valid, that it is still correct. Now, if you divide everything by 9.81, what would happen? So 2 times 3.15 divided by 9.81 equals 9.81 t squared divided by 9.81. So this 9.81 and this 9.81 will cancel out. I have 2 times 3.15 over 9.81 equals t squared. See, I am finding t. 9.81 t squared. I am finding t. I'm trying to get rid of things that are around t so I can isolate t and find it. I had 1 over 2, which was on our way, so I got rid of it by multiplying by 2. I have 9.81 on my way, so I divide everything by 9.81 to get rid of it. Now, I have, again, a equal sign that is still valid, because whatever that I did to the left-hand side, I did it to the right-hand side. Okay, now what I can do is to put everything under a square root. So I have 2.315 divided by 9.81 equals t squared. Whatever that you do to the left-hand side, you can do it to the right-hand side. Put everything under the square root, right? So on the left, you have square root of 2 times 315, 9.81. On the right, you have the square root of t to the power of 2, which is just t. So I found t. Simple as that. Okay, I found t. Put this in the calculator to see what you get. You should get something like this, 0.801. So t is 0.801 seconds. Part B is asking, what is the lemon's speed just before it hits the ground? So right before it hits the ground, what is its speed? Okay, we can use the time-independent equation. Yeah, we can do that. You can do that, or you can use different things. For example, you can use this one. So for part B, B equals AT plus V0. So V of final is A. A is just the free fall. So in free fall, the acceleration is gravitational acceleration, which is G. So this guy is G. So GT plus V0. What is V0? initial velocity dropped, it starts from 0. So v0 is just 0. G is 9.81, right? T is the time that it took it. We found it in part A. It's right here in front of you. So 0.801. Put this in a calculator, find the final velocity. So final velocity at this point is 7.86 meters per second. 7.86 meters per second is the final velocity. You might say, oh, isn't it the final velocity 0 because it just stops? Yes, eventually it will give all of the energy to the ground and it will stop. But at that point of a contact, when it hits the ground, it do it with a velocity, right? It do it with some sort of a velocity. And that's the velocity that we're talking about, 7.86 meters per second. Okay, you have two other problems here. I'm going to leave them right here. Again, dealing with free fall, freely falling objects with no other force other than gravity. You have two problems. Try to solve them. Try to look at the solution. If you have any problems, let me know. I can, I can talk to you over email, or I can, write down some stuff and send it to you. So try to solve these problems. Go over these problems a couple of times at least. It's important to master these, equations, master these, formulas, so you can easily, use them. I know that your major is not physics, and we're trying to keep that in mind that, you're not going to use these stuff after a couple of years, maybe even after like 6 months after taking this course. But I want you to, get the skills of it. I want you to know a little bit of physics after a couple of years. And the skills, one of the skills is that, not using a calculator as much as you can, getting it to the point that you have no choice to use the calculator, just like what we had here, for example. We put this in a calculator because in our head it's really difficult to calculate this. But try to avoid that as much as possible. Okay, so these are some of the problems that we have on book. Now I have assigned a homework for you. The only one last thing that I would like to talk about is that if you have a figure, VT figure, velocity versus time figure, and let's say this is that figure, okay? From this point to this point, from point A to point B. Point A has time TA, point B has time TB, VA, and VB, okay? If you can somehow calculate or find the area underneath this figure, okay? If you can find the area underneath this figure, okay, let me write it with this. If you can find this area will be equal to delta x, will be equals to delta x, to displacement. Okay, this is the displacement. If you have a VT, velocity versus time, then the area underneath is the displacement. So calculate the area inside a shape, right? A triangle, you have if it was a triangle, you know how to find the area of a triangle. If it was a rectangle, you know how to find the area in a rectangle. And that area will be your displacement. Okay? If you had an AT figure, acceleration versus time. Let's say a figure like that. Okay, from point A to point B. T of A, T of B, and acceleration, kind of like that. If you find the area underneath, this area will be the change in V, or delta V. So have these two in mind. These are very important piece of information. Okay, let me know if you have any questions. This is the end of week 1. No, this is actually the Monday. So yeah, let me know if you have any questions.